this chapter, we're going to study different statistical distributions. This lesson will be a very brief introduction to the normal distribution.
Okay, hi everybody. So now we're going to take a look at a chapter on statistical distributions, and right now we're going to introduce the normal distribution. Okay, now this is as the distributions go, and there's lots of different statistical distributions, and what we mean by that is just the way data is arranged. Right? When you've got a collection of data, where is it clustered? Where is it kind of really thin? You know, where is are there very few data values? Where are there lots of data values? It's just, that's what we mean by that. So, like it says here, in many situations, the spread of data is such that the histogram is a bell-shaped one, like the one shown on the right here. So now, what happens here really, if you think about each of these dots here as kind of being the midpoint of the center of a bar on a histogram, and you connect them all together, if you make the class intervals on a histogram really small, then by connecting all those midpoints, you get a curve that looks more and more like this bell-shaped curve. Okay, and it has got some very specific properties that make it quite unique. We call it the normal distribution, quite honestly, because most just normal human populations, if you pick a trait that you can quantify, it's probably going to be distributed this way. So normal, because that's what we would expect. Okay, this is how we expect data in a lot of cases to be arranged here. Now, it's an interesting thing that if you've got data, or if you've got a population that typically is distributed a little differently, it's a neat kind of trait of populations that usually the larger the population, even if technically it's distributed usually in a different way, the larger the population, typically the more closely it approximates a normal distribution. Okay, so in smaller populations you might not get this nice curve showing up, but if that population gets larger, typically it will. Okay, so now let's take a quick look at some of the properties of the normal distribution that make it what it is. Well, first of all, the mean and the median and the mode are all the same, and they show up here right down the middle of that distribution. Okay, because 100% of the distribution lies below the curve, the total area below the curve is 1. So now what hasn't been stated here typically is that when you're dealing with this bell curve or this normal distribution, and there is a very specific function that creates this curve. Okay, we do have an equation for it. It's a little complicated. We're not going to worry about that right now because we've got other tools for analyzing it. But what happens here is it turns out that the area under the curve, okay, is equal to the probability, okay, of being, whoops, oh man, my spelling is atrocious, of being in that interval. So what I mean, whoops, you can't even see that, being in that interval. So what I mean is, let's zoom in on this. Let's say that this is my normal distribution here. If I pick two values right here and I say, well, what's the probability that somebody in the population is between these two values here? If we could figure out the area under this curve between those two numbers here, those data values, that would be the probability, okay, that data value is in that little region right there. So area is equal to probability. So something to take note of here as we go through this. Now, because 100% of the distribution lies below the curve, that means the total area under the curve is going to be 1. Now, the data is symmetric about the mean. So you've got 50% below the mean, 50% above the mean. Okay? Now, here's what is truly amazing. Okay? I mean, this is so cool. The fact that this pops out is amazing, and it really inspired people to have a good hard look at what's going on here. Because what we know is, if you've got a normal distribution, everybody, and you drop the mean right in the center here, if you take and find the standard deviation of that population, and then you mark off a little data value here, one standard deviation above, one standard deviation below, well, then it turns out, as long as that population is normal, then I know that 68% of the population will show up between those two. Now, it's not exactly 68, but it's really, really close to 68, okay? If you go 2 standard deviations out, so add a standard deviation, add another standard deviation, subtract a standard, subtract 2 standard deviations, you mark off those values right here, well, then it turns out that 95%, or just really, really close to 95% of the population shows up in that region right there. And we can go out even further. If you go 3 standard deviations out, more than 99% of the population should be inside there. Okay? So by creating an interval that's 3 standard deviations below the mean to 3 standard deviations above the mean, in any normal population, you've now dealt with or encompassed more than 99% of the data. If we know that that is true, always true, of a normal distribution or a population that's normally distributed, we can make predictions about that population based on that. There are things that we know must be true about that population. And in fact, you're going to find in a little bit here, we can do better than the way that this is broken up right now. We can actually subdivide it even further by using a tool that we will introduce shortly here. But that is an amazing tool for being able to make predictions about how a population will behave. So let's just take a look at an example here, and hopefully you'll get a sense of what I mean by that. Okay, so here's our question here. So percentages of data within 3 standard deviations of the mean. Well, that's where we're going to go to in a second here. But it says the heights of the boys participating in an RIBT tournament here. That's a basketball tournament locally here. Are normally distributed about a mean with 180 centimeters. Okay, the mean right here. The mean is 180 centimeters. That's important to know. And a standard deviation of 5 centimeters. Okay, 5 centimeters. So that means on average, okay, on average, the separation that one of these boys, in terms of their height, the separation that they are from the mean is about 5 centimeters. So between what two values located symmetrically about the mean is approximately 68% of the data. Okay, well, I know that 68% of the data is from 1 standard deviation below the mean to 1 standard deviation below the mean to 1 standard deviation above the mean. So this is going to be from 180 minus 5 to 180 plus 5. In other words, from 175 centimeters to 185 centimeters. I know that 68% of that group are going to fall between those two heights. Well, what if I wanted to make a prediction and I wanted to be like 95% sure that I've got everybody? Well, that would mean going 2 standard deviations below the mean to 2 standard deviations above the mean. So that's going to be 180 minus 2 times 5 to 180 plus 2 times 5. Now that's easy to do because the math is pretty straightforward here. So that's going to be 170 centimeters to 190 centimeters. So I'm 95% sure, okay, that if I grab a participant in this tournament at random, they're going to show up somewhere between those two heights. But I can go even better here. 99% is going to be from 3 standard deviations below the mean to 3 standard deviations above the mean. So that's 180 minus 3 times 5 to 180 plus 3 times 5. Okay, that is going to be 165 centimeters to 195 centimeters. And now I'm like almost 100% sure everybody there is going to be somewhere in that range right there. If there is anybody that's outside that range, it's probably like one person. Odds are really low that you're going to find that one person, okay? So anyway, that's how you want to understand what's going on with this this normal distribution, okay? And those percentages there. Okay, and in this question it says, Okay, we're comparing distributions with different standard deviations. So the life expectancy graphs of 3 different brands of batteries are shown below. The same scale is used on each graph. So arrange the batteries, okay, ABC from smallest to largest standard deviation. Now remember that a standard deviation, okay, the standard deviation here, this is a measure of dispersion. Okay, in other words, it's a measure of the spread in the data. So the more spread out the data is, the larger the standard deviation. Now, a really good way of judging this is when you look at a curve here, okay, and you follow the curve here, when the curve changes from being an upwards curvature to a downward curvature, that point that's kind of in between here, that distance is roughly a standard deviation, okay? Roughly a standard deviation from that point to the median. So right here, I don't know, about right there, standard deviation, right there, standard deviation. Okay. Now, this is maybe not the best diagrams to really illustrate this, because what's happened here is things have been adjusted a little bit so that you can actually see what's going on here. But typically what happens here is if the size of the population is standard, okay? So what I mean by that is, let's say that each group of batteries here was like 100 batteries. Then when the peak is small, that means it's wide. And when the peak is tall, that means it's narrow. So as long as the population is standardized, the height is going to be related to the width as well here. And so what happens here is this right here should be the smallest standard deviation. And this one here should have the largest standard deviation, because this should be technically more spread out. And because this has got kind of a peak in terms of the frequency here, this is going to have a smaller standard deviation. So the standard deviations should be B, then C, then A. Okay? At least that's how we want to understand that. Right now, if you were to take and just measure that, you'd probably get the same values because of the way that the diagram was created here. But that's not how we want to look at it. In fact, it might be better, even more informative, if you looked at it like this and you had kind of come out like that, and then kind of a peak like that. Okay? Now, let's actually, here, I'll throw a question out for you right now. Let's say that these represent, this is going to be your frequency. And let's say down here are your marks. Okay? The marks in a student's class here. So the question is, which class, A or B? Okay? So we'll ask it like this. Which class has the higher, or let's say the larger mean and the larger standard deviation? Okay, well, the mean is going to be right down here through the center here. Okay, mean. Now, it would be very tempting to say, well, this one has the larger mean. Look, goes up here. But that's not actually how you measure the mean. When the mean is a mark on the x-axis, its size is measured by how far away it is from the y-axis. Okay? The number that's further along on the x-axis, that's the one that's larger. So A here, A has the larger mean. Okay? It's further over. Now, which one has the larger standard deviation? Well, which one is wider at the center? Well, again, it's A. A has the larger standard deviation. So not only is the mean further over, so it's a larger average, but it's got more spread in the data. This has got a smaller average and it's a smaller standard deviation. There's much less spread in the data here.